Lecture 2 for General Chemistry 1. So traditionally we divide chemistry into about the about is on purpose, about 4 different main branches. One of those is called analytical chemistry, and it's really kind of my favorite, but this is about the precision and the ability to replicate results, stuff like that. It gets into the plus or minus of things, the standard deviations and all that. In Gen Chem, we take just a really, really small bite of this idea just to get you used to what's really here. So we'll do some units, some canceling stuff, and I really hope that I can get you by any reticence on that. It really is a great trick, and it works in more than just chemistry. It's probably the best trick in all of science. And then we'll talk a little bit about significant figures. I'll often abbreviate those as SigFigs or just SIGs. So there are a lot of rules to SigFigs, but I just want you to know ahead of time that the SigFig rules are really the easy way out. So we've digested it a lot to give you an easier method than what we actually do in the hardest core bits of analytical chemistry, which has to deal with error propagation and hypothesis testing and overlap of distributions and stuff like that. So really, really deep in the stats. But here we're just going to make some simple SigFig rules, learn to use them, and go forward. So one of the things that you have to be proficient with is scientific notation. If anyone is interested, I can help you find where these are back in your middle school and high school maths standards. So they should already be in your toolbox. So if not, there's some coverage of this in Appendix B of your textbooks, kind of review of scientific notation, how it works. Also, this would probably be a wonderful, wonderful thing to take to the math lab. If you want to do some review, get to know those folks over there, it's a really good idea to go get to know them early so that you've got helpers when the time comes later. You can definitely come to me with this, scientific notation. And technically, I use something else called engineering notation sometimes, but I try not to use it as much in Gen Chem because I don't want to confuse y'all. But if you just get proficient with this thing, it'll make life easier, especially in the sciences. And here's the why. So we talk about stuff in grams a lot of times, and so if we talk about 12 grams of carbon, well, we happen to know from those experiments we were talking about how many carbon atoms that is. It's we're going to do a lab hopefully on this semester and try to estimate this number. It's Avogadro's number. I don't even know what the quadrillions, quintillions, whatever that is, name for this number of zeros would be, because we never say it this way. So trying to write all of these zeros, especially without the commas. Y'all know that the Brits use commas apparently for decimal places. And so we can't just use the commas because that gets confusing if you're talking to somebody from across the pond. So then you just start writing this like string of zeros, and nobody's sure how many zeros anybody writes without actually individually counting them and stuff. You can't do that all the time. So there's actually an easier way than this. We just write it as 6.022. Here's your 6022 times 10 to the 23rd. Now, if you count from here back, you'll find that if you move your decimal place all the way back here to the front of the 6, which is where it is here, that's 23 decimal places. So that's what this number means. 6.022 times 10 to the 23rd. It's just this longer written number up here. They're exactly the same value. You could also go the other way. The mass of a single carbon atom we could talk about it that way. And it's this number right here. Now we don't have the advantage of commas because you don't put commas in a decimal notation, right? So now we got to go the other direction. But now look, it's a big point here. 10 raised to the 23rd power. That's going to be a very large number. And in fact, that's why so many zeros out here. But now, this, instead of being a very large number, it is a very small number because 0.0000, a whole bunch of zeros, right? So that's a very small number. So instead of a positive exponent here, this one's going to have a negative exponent. So it still works that if you count the places all the way down through here, so that you move the decimal place to just after the 1, which is where it is here, then you get 1.993 times 10 to the negative 23rd. It's still 23 places. It's just the negative means it's a very small number, 10 to the negative 23 versus 10 to the positive 23, very large number. Or if you'll remember back to your exponent rules from algebra class in high school, a negative exponent just means that same number as a denominator in a fraction. So we could take a number. Here we have 568.762. We can convert that into scientific notation. So we want to have that single digit to the left of the decimal. So I need to move it how many places? So I count them. Like, well, 1, 2 places here, right? So it's a big number, 568, not some small decimal number. Therefore, I'm going to expect my number to be greater than 0, and it moved 2 places. So 10 to the positive 2, and then it's 5.68762 times 10 to the second. Okay, let's go the other direction. Let's look at a small number. Now this one's going to be a small number, so what do we expect from that? That we're going to move the decimal to the right. It's going to be a small number, therefore the exponent is going to be a negative number. N is less than 0, which means a negative number. All right, so let's see how many places do I need to move it. I need to move it 1, 2, 3, 4, 5, 6 places. All right, so I'm going to get 7.72 times 10 to the negative 6th. Okay, addition and subtraction. So to subtract or add scientific notation, you need to get so proper scientific notation says one number to the left of the decimal, and non-zero number to the left of the decimal. But for addition and subtraction, we need to get it out of proper scientific notation sometimes in order to have the same power. So I've got to change them such that the ends, the exponents on the 10, are the same. And then I can just add and subtract and keep that exponent where it was. So example, I want to add these two numbers, 4.31 times 10 to the 4th plus 3.9 times 10 to the 3rd. Well, they're not the same. So we could actually change either one of them. So what I have done here is I have decided to go with the 4. Now, 3.9 times 10 to the 3rd is the exact same thing as 0.39 times 10 to the 4th. So here I have made this part of the value smaller by going from 3.9 to 0.39. made it smaller by a factor of 10. To keep everything equal, then I've got to make it greater by a factor of 10 over here. So that goes from 10 to the third to 10 to the fourth. So that this piece, 3.9 times 10 to the third, and 0.39 times 10 to the fourth are the same quantity. They are exactly the same. Now I've got my fourths, a 10 to the fourth in both cases. Okay, well, cool. Now I can just add my numbers. 4.31 plus 0.39, and I get 4.70 times 10 to the fourth. All right, so that's how addition and subtraction works with it. Now, as is often the case, multiplication and division are actually easier with scientific notation. So just multiply the number parts, and then you add exponents, because remember, rules of exponents, when you multiply like bases, you add their exponents. Okay, so if I want to multiply these things, 4.0 times 10 to the negative 5 times 7.0 times 10 to the positive 3. All right, so what am I going to do? I'm going to multiply the 4 times the 7, right? And then I'm also going to multiply the 10 to the negative 5th and the 10 to the positive 3rd. That just means add those exponents, the negative 5 plus the positive 3. And I get 28, 4 times 7, times 10 to the negative 2, because negative 5 plus positive 3 is negative 2. Now, do be careful with this. Let's see, 28 times 10 to the negative 2 is fine. It's just, it's not technically in proper scientific notation yet. So I need to, where's my decimal at here? It's after the 8, so I need to move it one more place like that. It's going to make that a smaller number, so we need to make that a bigger number, so go up by 1. So 2.8 times 10 to the negative 1. And again, if you want to practice that, Math Lab will help walk you through these step by step. You should practice them a lot. Hopefully you already have. Hopefully you've already practiced this so much you're sick of it in high school, and now you're great with it and you don't need to. But just in case, I'm going to be giving you a lot of these on exams and classwork and stuff like that. So you should practice them somewhere. Division works just like multiplication. So they divide the numeric parts, and then so when you multiply, you add exponents. That just means when you divide, you subtract them. Don't get confused by the positives and negatives on that. 8.5 times 10 to the positive 4th divided by 5.0 times 10 to the negative positive 9th. So that just means 8.5 divided by 5, and then also 10 to the positive 4 minus the positive 9. So it gives you 1.7 times 10 to the negative 5. Now, I strongly recommend that you practice these and then also practice them with your calculator. So you don't have to spend time on an exam worrying about this. So you're so proficient, your calculator knows how to do these, and as long as you know what to tell your calculator in doing these, then it all works out. Let me give you one particular caution, and that is that sometimes your calculators will take over with order of operations, and so it's always a good plan, especially where you're dealing with division. Let's say we've got 3e5 divided by 2e2. All right, so here's what you don't want to happen. So really, let me change colors here. This part is exponential, right? So if you just type this into your calculator as one long string, what you don't want is for your calculator to think, let's see, I see 3e5. That's an exponent, so PEMDAS, I'm going to do that first. So I've got 30,000 there, okay, divided by 2, and I'm going to get 15,000. All right, cool. Oh, and then exponent 2, I'm going to do that somewhere else. Don't risk it. I think this one would actually work out okay, but do this for me. 3e5, and in your parentheses, in your calculator, just start with a parenthesis. do open parentheses, 3E5, close parentheses. Divide, open a new parentheses, and do 2E2, close parentheses. And then you've taken back control of this and made your calculator do precisely what you want it to do instead of hoping that it works. So chemistry is about a lot of measurements, especially that analytical branch that I was talking about. We measure things. This is what we do. Enjoy doing it. So measurements give us the basis to make the hypotheses, theories, and eventually, hypotheses and eventually theories. Sometimes the laws that lead us to, it does this, and we're not sure why. So we've got different information when we make a measurement, right? So you have, I'm going to skip down here to 2 and start with units. Whatever you're going to measure, and you've got to decide your units, right? So choose the units that work for what you're doing. If I'm surveying in a cave, then I'm probably going to be surveying over here, probably going to be surveying in feet, except with some of my younger friends tend to survey now in meters. Either one of those works well for in cave. You don't want to survey a cave in inches, at least at my age, not any cave that I want to be in if it needed to be surveyed in inches. Feet is a whole lot more appropriate unit. But if I am cutting wood to build a piece of my deck, then I do want to measure in inches, probably. I wonder in the metric system, I don't know this already, in the metric system, I wonder if they do that in centimeters typically. I would guess so. So anyway, it depends. Choose a unit that goes with. So you want that for a measurement, and then you're going to get some numeric value. Maybe you're gonna cut a board to 32 1/4 inches. So 32 1/4 is the magnitude of that measurement. Now, here, this third piece, we often just leave it off, and maybe we shouldn't. But so if I tell somebody to go cut that board 32 1/4 inches, how much precision am I expecting? Well, it probably depends on what I'm doing. If I'm framing a house and it's 32 1/4 plus or minus 1/4 inch, it's not going to matter a bit. That's going to be perfectly fine. But if I'm building a cabinet and it's off by 1/4 inch, that does matter. So we need to know the plus or minus that goes with the level of uncertainty or the required level of uncertainty for a thing. All right, I'm going to spend a lot of time here talking about units. So, things can get confusing if you don't put your units. I actually saw a sign that said this, and I resisted the urge to drive back and forth in front of this sign in order for somebody to give me a ticket so that I could go fight it. I didn't do that, but this sign has no meaning. Speed limit 55. Well, 55 watts. Meters per second? Okay, cool. Speed limit here is 55 meters per second. That's going to be fun because that'll convert to 123 miles per hour. Now, yes, we probably all know that speed limit sign probably means 55 miles per hour, at least here in the States. But technically it has no meaning without putting units on it. I didn't risk it. So I don't know if a judge would agree with that or not. It's kind of 50-50. So in chemistry, we use an updated version of the metric system. It's known as SI, and apparently the SI version, there's International System in French or something. But we've been using that since 1964. So use the units that work for the job you're doing, right? I am so used to the metric system. I use it all the time. But honestly, if I'm cutting that wood for the porch, I'm still using inches. That's what my tools are calibrated in here in the States. If you're trying to use centimeters, and if you're doing really technical work, now you got to worry like, well, okay, well, what's the kerf size on my saw? I know it's a 1/4 inch, but what is it in centimeters? So just use the units that are appropriate for the job that you're doing. In chemistry lab, that's going to be the metric system. So we're going to use the metric system almost exclusively. All right, next important piece about units, and that is base or fundamental units. Okay, so it's a little bit confusing. Base units are technically these 7 base units over here: meters, kilograms, seconds, amps, degrees K, moles, and candelas, or lumens is starting to be used more than candles now. They didn't ask me. I would have done it instead of kilograms. I would have made it grams because I think that's more consistent, but that's not what the official version is. So, a fundamental unit, I'm going to use it for a slightly different. I'm going to use it for these guys over here that I wish they had asked me about. There's a link down here to all the real rules, how NIST, National Institute of Standards and Technology, I think is the T. But that's the U.S. clearinghouse for how this thing is supposed to be done here in the States. So that's where the real rules are. We're gonna work from basically these units don't have any modifiers on them. So meters is not nanometers; it's just meters. And so I'm going to claim that grams is one of these quote fundamental units, which is not real well defined. All right, so the SI base units. So we've got these 7 different things, and I'll talk about derived units in a bit. But these are the 7 things that we think we can't make up from other units. So these 7 we've got to have their own measurement for. So length we've got to measure. We can't get length from anything else. It's not made up of anything else. So we're gonna define a unit for it. It's the meter. It's approximately equal to 3.28 feet. You can get a more precise value than that. Symbol is a lowercase m. All right, mass. The base unit in the metric system is the kilogram. It is modified kilo, but it's 1,000 grams precisely. Now, technically, there's a unit for mass in our Anglo-Saxon system, but it's not pounds. Pounds is actually a measurement of force, and it has to do with how much gravity is pulling on a mass, and it changes. At the surface of the Earth, a kilogram of mass has a weight of about 2.2 pounds, but really, mass-wise, the unit, it really is, I didn't make this up, the unit is slugs, and so 1 kilogram is 0.0685 slugs. Time, we measure in seconds usually. Temperature in degrees Kelvin, and we'll spend some more time talking about temperature in a bit. We won't use amps very much, especially in Gen Chem 1. They do come back a little bit in Gen Chem 2, but amps is a measure all its own. And then I'm going to skip down here to luminous intensity. You probably won't see this one again unless you're taking some physics courses, or my chemistry majors, you may see this, or more likely lumens nowadays, in physical chemistry, where we actually start measuring how many photons are incident on something and stuff like that. Now back to the 6th one here, an amount of substance, the mole. The mole is going to be a big deal for us, and we're going to talk more about it. All right, so prefixes. Now this is one of the reasons that the metric system does work a lot better than our Anglo-Saxon systems. This is similar to a table on table 1.3. And I keep using these page numbers because I'll go from the PDF of the textbook, but it is still table 1.3 even if you're just using the online version. So they give you fractional or multiple units, right? So meter is our base unit for the metric length system, right? Grams, I have base marked out because I'm going to say it's the fundamental unit. Liter is a fundamental unit for volume. And so what this 10 to the 0 means is, so if you raise anything to the 0 power, as long as it's not 0 itself, it's just 1. All right, so just the meter symbol by itself means 1 meter, 10 to the 0, or 1 liter, or 1 gram, or whatever, right? But if we make smaller versions, like when we were talking about the size of that nucleus earlier, right? Well, we can't use whole meters because 0.00 is a whole bunch, right? So we tend to use nanometers, 10 to the -9th, right? And we do that by putting an n in front of it. I'm going to show these in a second. Or picometers, 10 to the -12th. But instead of using all the 10 to the -12, 10 to the -9 all the time, we start to hang these other things on it. Now that seems like a lot of extra work, but once you start doing it a lot, right, then it starts to creep in and make a lot of sense. Instead of all the time saying if I'm measuring something, if I'm in Europe and I'm cutting those boards, and I keep saying, oh, go cut the board to 32 times 10 to the -2 meters, it actually is easier to say 32 centimeters. Same idea here. That's why we have these prefixes. All right, so here's what they are. So this deci prefix means 1/10 of, or 10 to the -0.1. So that's what deci means, or centi, 0.01, 10 to the -2, etc. Now, after you get past deci and centi, it gets easier because they go in threes. You see how this is -1 and -2. But then after that, we go -3, -6, -9, -12, -15. And it gets these names on it. So you have a decimeter, which is 1/10 of a meter, 1/10 of a gram, 1/10 of a liter. You can do the same thing with centi. Centimeter is 1/100th of a meter. And the rest of these. So here's our nanometers that I was talking about earlier, or our picometers, right? And that's what they mean, is a very, very small unit of length. And just like you can use prefixes to make very small, you can also use prefixes to make very large. Kilos, 10 to the 3rd. Megas, 10 to the 6th. Gigs, 10 to the 9th. Teras, 10 to the 12th. And if any of you guys are used to computer terminology, the prefixes are the same. Now it's slightly different numbers, because if you really get into it, 1,000 kilos is not a meg, it's 1,024, just to make, because it's base 2 system. In metric system, it's all nice and easy, base 10 system. So you say 1,000 kilos is a meg, 1,000 megs is a gig, 1,000 gigs is a tera, and keep it simple. So a few of the more important base units and how we define them. So originally, the meter was intended to be a fraction, 1/10,000,000th of the distance from the North Pole to the equator. It didn't really work out, and turns out that the planet bulges and changes, and so that doesn't work as well as they had expected. So now, modern, we actually tie it back to time and to the speed of light. I think this one may end up having a problem sometime in the future now that we know more about how light works. But anyway, A meter for right now is defined as the distance that light travels in a vacuum in this very, very tiny fraction of a second. So that's how we define a meter now. It's about 3 inches longer than a yard, about 39 inches-ish. I'm only going to do a few of these, but mass is defined. So the base unit is the kilogram, and originally it was defined as the mass of 1 liter of water, and we still use that as the most common definition is one liter of water. Technically, though, water does change density with temperature, especially a little bit with pressure. So that doesn't work perfectly well, but it's about right. Then they decided that they would change. They would define it by a certain platinum iridium alloy that they kept in France. Well, but that has problems too, because now that technology has gotten to the point that it has, we can actually measure things more precisely than even this platinum iridium cylinder was able to maintain, depending on the temperature. So they had to say, well, you have to measure it at this temperature. Oh, well, you have to measure it at this. You have to hold it at this angle relative to the Earth's gravity and stuff like that. So now the most modern that we have is this is a strange definition where you use the Planck's constant, which is the same everywhere in the universe, and then you express it in joule seconds, and then use that to derive the unit of mass. I mean, it's complicated to do it that way, but the cool thing is that using modern technology now, it can be redefined anywhere in the universe instead of having to go back to France. So it does help some. Mostly in chemistry, we're going to do things in grams or milligrams instead of kilograms. Please do not set up any reactions in the lab to use a kilogram of reagent. That's really expensive if you do that, so please don't. And one more base unit to talk about is temperature. So when you get to Gen Chem 2, it becomes even more dramatic that you have to use Kelvin instead of the other temperature units. So Kelvin is this base unit that we use. So you can use C, and you will see that we use it a lot of times. The reason we use that is it's more common to our temperature experiences, I should say. And Kelvin, though, Kelvin is really, really better. So, little bit about the degree symbol. You will probably see that I tend to not write the degree symbol. So, technically, I'm wrong when using C. I should put the degree symbol, but I'm probably not going to. If I want to write here 100C, I'm probably just going to write 100 space capital C. Technically, it should have the degree symbol. That's not true with K. 273.15K is actually the accepted way to write it. So for me, you don't have to worry about putting the degree symbol, but over here I give you a note that might or might not be true if you take somebody else's other chemistry class. So one final thing is that the C temperature and the K temperature, the size of a C temperature unit and the size of a K temperature unit are precisely the same size. They are 1/100th of the temperature difference between boiling and freezing water at 1 atmosphere pressure. Okay, so in physics, we claim that there are those 7 base units that I introduced earlier. Those we've got to have. We've got to define everything according to those. And then everything else is just derived from those 7 units. Example, area. Well, you know what? Area is really just a length on one side and a length on the other side. So really it's just derived from two length measurements. And so we use the square meter as the unit for area. Same thing for volume. It's just three of them. It's cubed, right? So, or you can have them that mix units, like speed or velocity are measured in meters per seconds, or meters divided by seconds. Accelerations, meters per second squared, etc. Remember what the negative means? It just puts it in the denominator. So this is the same thing as, let me change that to a pen, I'll write it. This is the same thing as writing 1 over meters. Just like this is the same as writing meters over seconds. Or I was teaching a physics class recently, and I tend to write it sometimes as meters s minus 1. So that minus 1 part just puts the s down here in the denominator, just like it did with this meters here. It's the same thing. Another thing to just be used to. You'll see me do it. These are all just derived units or combined different units to make something, to make another measurement that we need to be able to make. So an example of a derived unit. So energy, the amount of energy that we could measure, is the units that we use is the joule. It's abbreviated as a J, Joule, guy's name. So 1 joule is an amount of energy, but it's not a fundamental unit. So this joule thing must be made up of other units. In fact, 1 joule is defined as 1 Newton meter. Newton times meter, and Newton is a measurement of force. Meters, you know what are, but now wait a minute, Newtons are not one of those fundamental units either. So they must be derived from something else. And indeed, the full definition, a Newton is a kilogram meter per second squared. And then you still got that red, that one I've coded red here, the meters, right? So you can staple all this together and say that 1 joule is equal to 1 kilogram meter squared per second squared. Okay, so I'm finally looping back around here to the idea of measurements, right? And so we have to talk about precision and accuracy. And here's the traditional example of targets, right? So you could have precision here in the middle without accuracy. Precision is how close together, or it's based on the standard deviation. If you've had a statistics class, smaller standard deviation is more precise. Accurate is whether or not your values, regardless of whether they're precise or not, but whether or not they cluster around a, quote, true value or an accepted value. So I wanted to work out an example here to show you what I mean by that precision versus accuracy. So EPA says that for arsenic in drinking water, the acceptable level is 0.010 milligrams per liter. So we have several different analyses here. Now let's say that we know somehow that the true value is really 0.3135 milligrams per liter. Let's say I've taken some samples and given it to students in an environmental chemistry lab to analyze, right? So here are the 3 different sets of measurements, right? So what we would do is we would take and we would do the statistics to these different sets of values. We'd do an average, we'd do a standard deviation, and then using the standard deviation and the number, we'll figure out what's called a confidence interval, or a plus minus, right? So if you work these through, if you average all 4 of these values, you get 0.310 milligrams per liter. If you ever see me do this with this subscript, see the 0 on there? That subscript means that that last value is not significant. So significant figures is going to matter so much to us in this course, right? And there is where that SigFigs comes in, right? So I'm saying this only has 2 significant figures. That third one is subscript because it is not. So I'd work a standard deviation. I'm going to show you how to do that in one of our labs and use that to do a plus or minus on it. So that's set 1. Let's see, what do we have here? Those are our different values for set 1. Now set 2 looks like their values are closer together, right? So look at what it did to the standard deviation. It's a much lower standard deviation and plus minus. The average is in a different place also. So let's look at that. So this one hits really close to the accepted true value, right? So this student did pretty well on getting the right answer. However, their measurements are kind of all over the place, and so their standard deviation was pretty terrible here. This one got like right spot on same measurements, but their measurements are all clustered around the wrong spot. And set 3, we have, well, their values are kind of a little bit random, right? 0.058 standard deviation, and also not in the right place. So what we have here is we have set 2 is an accurate, set 1 is an accurate but not precise set of measurements. Set 2 is a very precise set of measurements, but it is not accurate. And then set 3, of course, is just terrible on both. It is not precise, it is not accurate, it is just all bad. And then, of course, there's an implied 4th set. Here's my star student that has like, extremely precise and spot on. Average-wise, very happy here. This is both precise and accurate. All right, so measurement uncertainty, and this is where we're sneaking up on the idea of SigFigs. So what's the volume in this depiction here for this graduated cylinder, right? So if you just say, well, it's 20 mils, you can do better. You can do better than that. I mean, look these lines here. They give us graduations, right? Let's see, 1, 2, 3, 4, 5. Oh, okay. So each one of those lines is another milliliter. Oh, okay. Well, 21 then. Still, you can actually do better than 21. Looking at that, that's not spot on the 21, right? So it's not right on the 21 line, and it's definitely not on the 22 line. It's actually like in between here. So you need to make an estimate between those. So what are we going to estimate that as? I would not agree with this being 21.9. I would have probably called this 21.4 milliliters. 21.6. Okay, I can. If you read this as 21.6, I think that's fair. I would have probably said 21.4. And the more important thing than agreeing with my measurement is agreeing with your own measurement over and over again, being consistent in the way you read that value in that. Okay, now SigFigs. We'll finish up with this. Let's see, SigFigs. So this is how it works. The rules. There are rules. So any digit that is not 0, that's going to be automatically significant. So that guy's got 4. Zeros that are between non-zeros, they count as significant. So 606 has 3 significant figures. The 6's are, and then the 0 in between. Now it gets a little more complicated with the other zeros. Zeros to the left of the first non-zero digit are not significant. So here, 0.08 liters, well, only the 8 counts as significant here. I don't agree with this statement. It's straight from your book. And so, well, I'm sorry, this one's okay. If a number, then all zeros to the right of the decimal point. Yes, okay. So trailing zeros are significant. Let's see. That one's fine. So the problem with this statement here that I was complaining about is 30. How many SigFigs does that have? All right, so there is some disagreement with this, but in my book, this has one significant figure, just the 3. So the trailing zeros are not. Now, so put 1 sig. But if I put 30.0, why did I write this? Well, I must know it. So this has 3 sigs. Okay, so that's the tricky part. All right, addition and subtraction of significant figures. So the basic idea here is to line them up. So shift it around and line it up so you add, you have to put your decimal in the right place here, right? So I've got 89.332 plus 1.1-ish. I don't know what these decimal places out here are. Therefore, my answer cannot have these decimal places anymore because I don't know that this is 1.100. It could be 1.101. Therefore, that would change this 2 value out here. I can't have that anymore. So I can only have that furthest decimal place. And so 90.4 is all I know at this point. That's your rules for addition and subtraction. Subtraction works the same way. Line up the decimal point. So all I know is 70. I don't know 70 what. So same thing. I'm going to have to round off my answer to 0.79. So just like with scientific notation, of course, multiplication and division is easier with SigFigs. You just look at how many SigFigs you have on all your measurements, take the smallest of those, and go with it. So this multiplication, well, the 4.51 has 3 sigs. That's less than the 5 sigs in the other number. Therefore, my answer is going to have 3 sigs. And keep it that simple. Now, look, I'm going to ask you questions that are going to make you have to deal with the addition and subtraction. But if you are a scientist, and later on in life, if you really need to do SigFigs, most people just use this as the shortcut. Figure out the SigFigs, the smallest number, and go with it. And that's not always right, but it's a shortcut that'll work 85% of the time. So 6.8 divided by some greater number of SigFigs, I need to have 2 sigs. All right. A caution about exact numbers. All right. Some numbers are precise by definition, and in that case, they have an infinite number of significant figures. So, for example, if I want to take an average of these lengths, so how many sigs am I going to have? Well, I'm going to have, they're all going to have 2 decimal places when I add them up. That's cool. Then I'm going to divide by 3, and some people would say, well, 3 is one significant figure, but it's not. The 3 is an exact number. You know when you know that you don't have 3.01 measurements, right? That's not a thing. You have precisely 3 measurements. So the 3 has an infinite number of significant figures, so we are constrained here to the addition rule and to 2 decimal places, 3 total. Well, it's going to actually be, 3 total significant figures, 6.67. Not 7. Be careful of that. So this video is already longer than I intended, so I've skipped a few slides in between. Y'all remind me to cover those with you. In class, I want to give you those as examples before we get started on the classwork for this section. And I wonder what the video does. It probably just skips through. I did want to come back to this one and talk about converting temperatures, just to make sure everything goes well for you there. So these are the temperature scales, and we're probably not ever going to convert anything to Fahrenheit, but here's what I do. I look for the known places. So the freezing point of water is one of those spots. Memorize these three values. So we know that water freezes at 32 degrees Fahrenheit, and we know that it freezes by definition at 0 C and at 273.15 K. All right, those are by definition. So we've got those spots. We also know that water boils at 212 Fahrenheit, it boils at 100 C, and it boils at 373.15 K. Well, given those, then I can always make a function to relate those values. And here's the relationship for them. So to convert from C into K, all you have to do is add 273.15. To go from K to C, all you have to do is subtract 273.15. Now, technically, there's a little bit stronger conversion down here, but this up here works. Just do this up here, and it will work for you. Add 273.15 to get from C into K. Okay. And then finally, if we do any Fahrenheit conversions, then here's your Fahrenheit to C conversion. You could take your Fahrenheit value, subtract 32, and then multiply that by 5/9. Go the other direction. You've got a C value, multiply by 9/5 first, and then afterwards you add 32. Order of operations matters very much here. And here's what I do. Is I know I've got 9/5 or 5/9, right? So I've got C. Well, 5/9. So let's say I'm converting 212. Let's say I'm converting something other than 212. I'll write my formula out, stick 212 in it, and make sure that my answer is 100, because I know 212 is the boiling point for water in Fahrenheit, 100 is the boiling point for water in C. And so if my formula is set up correctly, it'll convert 212 to 100 C. Or if I run the other way, set up my formula and make sure that it converts 100 C into 212 Fahrenheit. Then I know I've got it worked right. Then I can put my real value in there and see what I need to do with it. Where the parentheses are do matter a lot in this conversion. So, homework for tonight. So I hope that you have actually already read section 1.6. But look, it's going to be super duper important for the dimensional analysis that we're about to do, and that'll be in video lecture 3. So go ahead and look at that when you get a chance. Review your maths, especially those negative exponents and variables rules. We're going to be canceling, we're going to be adding exponents, etc. So make sure that you are really, really proficient in the maths. I don't want it to hold you back in understanding chemistry. And I'll see you in class.